Well, hello everyone in UST. Today I will bring you an introduction of Ansys Mechanical, which is the structural analysis software with the finite element analysis. Today's instructor, Danny Wong. Before we get started, here is my brief resume and the lecture material. And you can download with the QR code, or you can attach the material with the TA here after the lesson. And I'm the CA Senior Technical Assistant Manager, very long title, and from Cybernet Taiwan system. As you can see up below, we are Cybernet, and we are the Ansys channel partner. So, are you all scanning the QR code? So you can attach the material with the TA. No. So, there is a connection issues. I think we start the lesson. Here's today's agenda, and I will show you the instruction of Ansys Mechanical. And then we will show you how to do the structural analysis with Ansys Mechanical and with the problem, static structural analysis, and model analysis. And these two are the basic and the most fundamental analysis of the structure. Let's start with the instruction of Ansys Mechanical. But before that, we have, for common reason that we do simulate for. The first is, for example, we have to meet the aviation regulations in preventing of severe hazard, something like that. So when you are developing your product, you have to meet the product code regulations. The second is our product is visual experience in the test, like a structural test like drop, vibration, or thermal cycle, and act. And we will have to figure out the performance of our design or the root cause to failure. So when you are trying to validate your product design, or even you would like to improve the product performance and to validate the reliability, so you will need the simulation tool, because there are some root cause you are trying to figure out. It is hard to obtain some critical phenomenon through the experiment. You will need the simulation tool to validate your product. What's going on with the screen? And the development process should be economic. We don't want to spend too much time or money in solving problems, so we do need to do the simulations instead of the experiment in some scenario. Because sometimes the prototyping is too much expensive, like when you are trying to build up a rocket, when you are trying to experience with the prototype, and it very costly things. So you have to using the simulation tools and simulate the fluid dynamics or structural analysis or magnetic analysis instead. So that is why we do simulate. But why structural simulation? And our engineer, like mechanical engineer, we want to understanding the structural field, what happens in the products when they are undergoing load. All we want to do is the design validation virtually. We decide to know the mechanism in our studies, the performance of our design, or the root cause to failure of the product. And we want to know the stress or strain distributed on the products and the deformation of our mechanical design, the vibration event, and the total weight distribution. So basically, we were using the finite element method. This is the mechanical basic method with the analysis system is based on the finite element method. And it has several advantages in solving problems with complex geometry, material diversity, and 3D visualization result. As you can see, we can change the traditional way into the finite element method, and we can solve it more complexable problems. And with this software, we could evaluate our design virtually based on the structural basics. The general workflow is convert the 3D model, as you can see on the right top side, with the CAD tools. We can convert the CAD model into a mesh model, as you can see on the here. You can use some laser points. This is the mesh model. We will cut into very small dice into a mesh models, and we can solve it with robust solvers like Ansys Mechanical. And at the end, we can visualize the 3D results graphically. As you can see here, there is a red region with the high stress, and the blue region is the low stress. In structural analysis, our constitutive equation is as shown. As you can see, we do have 4 terms and 3 properties in the equations, which has the inertial force is dominated by the structural mass matrix, and the damping is dominated by the structural damping matrix, and the stiffness force, which is related to the structural stiffness matrix. And those physics properties, as you can see, is related to the accelerations, velocity, and displacement. And you can briefly using this 1 degree of freedom schematic in showing up the mechanism behind 1 node inside the mesh. In this specific analysis system, the equation could be reduced into an easy form, and we could talk about it later. Basically, we could catalog the structural problems into 4 types, depending on the nonlinearity and the type dependency. In today, I will show you the solution in linear static structural and model analysis. For the linear static structural analysis, as you can see, here we can divide the problem into 4 categories, with the static linear problems at the left top side, and the dynamic linear problems. As you can see, like vibrations, we can check the eigenvalue mode, harmonic, or probabilities. And for the static nonlinearity, we could consider about the nonlinearity contact, material nonlinearity, and multiphysics. For the nonlinear dynamics, there are some high speed or inertial force has highly nonlinearity into the dynamic event. So, well, in Ansys mechanical, in this kind of problems, the equation could neglect it. For the static structural problems like this, and we are solving the linear static structure like this problem. This is more easy form, so we can reduce the equation into the f equals kx. This is a very common form, but with the matrix form. In this kind of problem, we can neglect the inertia and damping force due to the steady result of this kind of problems. For the free undamped vibration problems, we could use the model analysis in solving the eigenvalue problems and calculate the mode and its shape. In this kind of problems, the equation would neglect the effect of damping force and the loading. As you can see, we can neglect the force and neglect the damping terms in modeling the linear dynamics and figure out the mode and the shape of the structural design. And in Ansys mechanical or in finite element method, we would using this consistent workflow in completing all the analysis. We generally divide the workflow into the 7 steps. In the next, we will have an overview experience on the user interface through the training course to application on structural analysis. As you can see, these 7 steps including the material definition, geometry preparation, meshing, simulation setup, and simulation execution, and result exploration, result comparison, and reporting. And in Ansys Mechanical, we do have a project manager, as you can see in the middle, and it is shiny, flashy. Why it's always doing like that? Okay. Okay, go next. So at first, we will demonstrate the static structural analysis. And first, we will know how to execute static analysis with Ansys Mechanical. I will demonstrate you during the course M01 to M08 in the lecture material. Let's see. In the lecture material, as you download, they will have include 9. As you download, you unzip the file, and you can see the material of this lecture. There is including 9 lessons in the material, and I will introduce you with the M01 introduction and the M09 linear dynamics in this material. And in the M01 to the M08, we will analyze a large globe bulb that is part of an industrial cooling system. It is already known that the bulb satisfying design conditions, but it is also required that the bulb be able to withstand forward loading conditions of 5 times the design pressure without exceeding 1/2 of its material ultimate strength. Then this product is including this structure is including the fan, the bulb seal, the bulb rod, bolt, and the nut components are all commercial items and have been evaluated separately. So you will focus on the bulb body component in the context of the overall assembly model. Your assignment is to determine whether the current design of the bulb body satisfies the specific fault limits for the governing boundary conditions. And in the lecture materials, What's going on? Okay. In the lecture, in the materials, we do provide and extra materials that you could exercise yourself if you do have a license, a student license maybe, and this part will not be included today, and you can practice by yourself. And about the model analysis in the M09, we could know how to investigate vibration characteristics through model analysis of a machine frame. And beyond of this lecture material, you could take a free course on an Ansys Innovation Space. It is a website. The link is as shown on this website. So you can just Google it with Ansys Innovation Space. You can have a limited but free student license for education purpose on this website. So if you want to practice it, you can use this website. And there are a lot of free learning resources on this website. It is free, but only for a 1-year duration of the student license. Please use it cautiously. It's only for education purpose. The free course is not only about the application of software, but about the fundamental engineering, and it is not only about structural analysis, but also about some other basic fields like magnetic and electric or fluid dynamics. So you can acquire more knowledge through it on this website. Okay, so we have finished the introduction of Ansys mechanical very briefly. And anyone have some questions about this? No. Okay, so let's get started with the static structural analysis demonstration. So, okay, skip the M00. So, let's start with the module 01. And M01, I will start Ansys with the demonstrating about the workbench, and which is the Ansys project management platform. And we will introduce you how to identify the geometry file to be used to open the engineering data application, and open the engineering data source view to manage your material, and describe the purpose of the engineering data source, about the material properties tables, and add the material through the EDS to the engineering data. And we will change the architecture system and check with the units of the project. And we will apply the loading and assign the material to the parts, and analysis to check if the result have exceed the limitation of the value. And the next, like as we said, we will add a fixed pole on the model and select the associated surface geometry. That is all we would like to do in this lecture. And there's too much word, and I would like to demonstrate to you instead of reading these words. So we can skip this part. But the most important is you have to figure out the answer of these questions through the process of during the process of the demonstration. There are 5 questions you have to ask by yourself. Ask to yourself, what does our part or assembly look like, and what is the part or assembly are made of, and how is the part or the assembly are supported, and how is the part or assembly loaded, and what do I want to learn about the parts or assembly. These problems you should always keep in your mind when you are doing the structural analysis. Okay, so we will answer these questions through the demonstration about assembly design. And there are some reference material, and you could access if you do have the software license, and you can access the Ansys help to figure out this setting instruction in the help. So we could skip this material, and after that we could turn it back to see this. So let's get started with the demonstration. As first, we will step by step. You can see the step-by-step guide in the lecture material M01 with name and with the PR01, the other one. There's an instruction of today. As you can see, we will solve these problems. In the Ansys mechanical interface, there are an outline tree. Outline tree, it manages every step you have made. And the graphic showing, as you can see, the purple one is your geometry constraint, and the red one is your loading. As you can see, graphically, you can get the information through visualization. And the next, we will teach you how to add analysis system within the Workbench interface. This is interface of Workbench. We will manage your product design process with this platform. And you can add analysis system through the toolbox at the left side. And next, I will introduce you how to import the geometry into the analysis system. And then we will know how to add a material or modify or add a material into the project. And the next, we will assign the material to the part and apply support conditions and control the view and apply the load. At the end, we will evaluate with the 3D result. Okay, it's quite quickly go through the process we would like to demonstrate to you. Okay, so let's get started with the first steps. So I usually keep my desktop very clean, and if you like to find out any applications, you can using the Start menu, and with the all applications, and figure out the Ansys 2024 R2, and browse down to the Workbench 2024 R2. I think you can figure out a platform and right click on the Workbench 2024 R2, and you can access into the Workbench. But somehow I would like to just search the work, and you can find out the Workbench 2024 R2 here. Please more quickly. And here is the platform we can manage our analysis or to any kind of project you want to analysis with. And we will start with the static structural analysis. We'd like to solve this problem with the static structural because it is static structural problems. And you can, using your left mouse, click on it and don't release it, drag to the green box and release your left mouse button, and you will create a new analysis system. And when you create too much analysis system, you can click and the triangle here and just delete the analysis system and press OK. It will delete this analysis system. And here we add static structural analysis for this project. As you can see, the title of this interface is called Unsafe Project because it is a project management in the platform. So we are managing a project. It may have includes a lot of objective of your product design. Maybe it would include the static structural, or maybe it would include the thermal issues, or maybe it would include some thermal stress simulation. So you can using this kind of connected, you can solve the thermal temperature and to evaluate the thermal stress induced by the temperature. So this project schematic. So this is the capability of this platform. And we can delete the extra analysis system. As you can see, we can step by step finish this analysis through 1 to 7. 1 is the name of this analysis system, and the 2 is about the engineering data. The engineering data means the material database only for this project. So we would like to check the material and to see what if we would like to add into this engineering data. But somehow this actually in the practical of the structural analysis or in the application, we would import geometry before define the material because we would like to know the geometry before we assign the new material to the part. So we can import the geometry first. And the data file is named with the ball body demo.scdoc. This file is a CAD file of Ansys form. If you do using other CAD tools generate the part would be STEP or something else. And in the material we providing to you, you can find out in M01 folder and find out a zip file here. You can unzip. Or because I do have unzip 1 here, and you can browse into and find out 4 files here. For demonstration today, we were using the ball body demo, the SCDOC. This is Ansys form. But I would like to show you the more common file with the .stp because you might have a lot of different kind of CAD tools, and there is a lot of different kind of CAD tools inside the world. And I will share the CAD file with the neutral file format. And commonly, we were using the .stp file to change our structural design to different kind of company. So we could turn it back to the workbench and right-click on the geometry and browse to the import geometry and choosing the browse. And you can copy the file path and browse into here and pass it. Okay. Choose the ball body for demo and open it. After you have success, the if here will change from 2 arrows into a check mark. And this check mark means that you have successfully imported your CAD. And after that, we can go the next step because the step is already done. So the next, we will add a new material into the engineering data for this project. We would like to add a material called gray cast iron. So here we can double click on the engineering data. And here, at the top view of the workbench, as you can see, our tab has become 2 tabs, and we will change to the A2 engineering data. And A2 means that you are in the analysis of A. As you can see, if we turn it back to the project view, and you can see there is A marked here, and it means we are at the A of the material is just like it in Excel. They will separate different kind of analysis system with different mark. And A2 means the A2 like Excel. It means A2 are assigned to the engineering data. And if you browsing into the tab, you can see there is a default material is called structural steel. And at the left side, you can add the property you will need to solve it for your problem. And the default, it will already add all the material, all the properties are required for solving these problems. As below, you can see the detail of the structural steel properties of the outline rules. As you can see, there is a density, there is a CTE, second CTE, and isotropic elasticity. For the extra, you would have assigned the SN curve or EN curve to this material and the spectral limitation of tensile yield, compression yield strengths, tensile automatic strengths to evaluate the failure, to mark the value of this material. But in this lesson, we would like to add the gray cast iron into the project material database, because in this project, it is only default with the structural steel, but we would like to analysis with the valve to using the gray cast iron, because this is the valve made of. But there is no gray cast iron, as you can see. There is nothing else. So there is some material provided in the workbench inside the material database. If you want to access the database, you can click on the engineering data source here. As you can see, I click, it will change the view into the material database view. And the table will divide it into 3. 1, 2, 3, 4, 5, 6, 6 view. And the first view at the middle top, you can see the engineering data source is the index of your material. And you can find out the general materials. And the middle of the view, you can see the list of the general material, outline of the general materials. You can browse it and figure out the gray cast iron here at the number 8. And if you want to add this material into your project, there is a plus here. You can just click on it. If you are success, there will be a purple book at the right side. And it means this material has added into your project. And you can turn off the material database here again through the same buttons and returning to the project material database. And you can see there is a gray cast iron have been added into your database, project database here. So we have finished the material edit. So we can end of this process and click the cross here. Okay. So after we have assigned the material and the geometry corrected, we have add a material into the project database and the geometry. After this 1, 2, 3 steps, the next 4 to 7 steps, we were using the mechanical interface beyond of the workbench interface. So if you right-click, double-click on the A4, you can access into the mechanical UI. So when you are starting the new UI, you will include your geometry and material information into this UI, and we can check it later. for the steps from 4 to 7, we will only use this AI, so we don't need to turn it back to the workbench interface. We can using this interface to finish all the next problems. As you can see, we can manage all of our next steps with the outline here, and you can move the outline to and where you want to put it in, or to automate to change the setting of the position. In outline, we will finish the unchecked items to make sure everything has been settled down to solve for the problems. At first, we would like to assign a material to this part. As you can see, we do have a geometry. I will check the material information of this part. You can click on the plus here to expand the tree of the geometry. You can see the part, it named with the component 1 body. If you right click and select the component of the component 1 body, and you can see the details of this part below the outline tree here. And here we sometimes we just to check about the assignment of this part. As you can see, we will default with the default material is called structural steel, and we would like to assign with the material in with the gray cast iron material within our project material, and you can click on the triangle at the right side here and browsing, find out the gray cast iron, and after that you have successfully assigned the material. So we will finish the material assignment very quickly. And if you would like to check the material setting by visually, you can click on the geometry and change the display style from body color to material. As you can see, here we will mark the part with gray cast iron with the color of the gray color. The color was assigned through the Android data here, and with the B column, you can assign the material color here. If you change the color into the green, here you can apply it and back to the material, back to the mechanical UI and refresh materials. As you can see, the color will change to the green. It seems a very unimportant function, but when you have a lot of parts, a lot of assembly, maybe 1,000 or 2,000, and if you can view the material information through this way, and there will be much more conveniency with the table here. You only can check one times a part. So this is very important things here. So we can check the material assignment and we finished it. And the next, we would like to put in on the support completions to the ball bodies. So all these function like material, coordinate system, mesh, we don't have to do anything on it because we would not like to modify any details in this project. They will be finished automatically. And if you would like to put in on the constraint to the structural analysis, and we will browsing to the static structural and select the static structural. And we would like to the fixed support here. So we can find out the fixed pole on the top of the tool. We can find out in the environment and put it on the fix. Okay, let's continue with the next. And as we talked previously, and there is some structural, there are some structure are not showing in the model, like flange, like bob rod or bob seal and bolted nuts, because in the single part analysis we would like to neglect it and simplify the model to reduce the time in solving these problems. But instead, we would like to keep the effect of this part and the stiffness of this part. So, as we know, there is a 7 megapart and the 2 megapart fluid pressure in the bodies, and the pressure would have a lifting force and lifting loading upward to the bob seal and the flange. So if we would like to simplify this model, we will reduce the geometry of this part, and instead with the loading on the flange structure on the bob body. So let's get back to the model. Beyond of these two fixed supports here, it is connected to the pipe neighbor to these bob bodies. And beyond of the pressure inside, we will need to apply the force here with the 9,600 Newton on the green region, because we would like to keep the effect of the bob rod and the bob seal and flange to these parts. So let's get finished of this loading and constraint settings. So the next, we would like to put the pressure inside of the bob bodies. As you can see, there is a lot of region that will have a pressure on it, but there are some region it is on C. And if you would like to view this part with different perspective of view, you can using the middle of the mouse and press it and moving your mouse, and you can rotate your part and view it with different angle. And you will, if you would like to shifting, moving, you can press Ctrl and combine with the middle button of the mouse, and you can shift your part, and you can rolling your mid button, and you can zoom in or zoom out. Okay, this is how we manipulate, operate our view control. Zoom to fit, and pan, and rotate. Okay, the next we would like to select all the internal surface, because the water would go through it and the pressure would have applied on it. So you can using the selector here. If you want to select the whole part, you can using the body. And after the selecting filter, you can click on the body and you can select the whole body. If you like to select on the specific surface, you can use the drag selector and press it, and you can only select the surface and the line and the dot and the vertical. the vertex. So when you are trying to select the surface inside, you can press on the surface and double click. It will extend the selection and rotate to the next side with the control and double click. You can select it, extend it, and the middle. So after you pick up all the internal surface, you can find out the pressure here and apply it. All the surface will apply it into the pressure settings. So when you have finished all the settings, the only left movement is to input the number of the pressure magnitude. So you can press 7 and enter, and we will input the 7 megapart into the pressure settings. So we'll finish the pressure apply. So after that, we have finished the selection and pressure apply, limited, extended. Oh, they are using the 3 megapart with different tasks. So we did for the 7 is for the different situations. So we can put, we correct it with the 3 megapart in this material. So the next, we just mentioned earlier, we would like to apply the force on this region. So we can select in the best selector and pick up the surface here and find out the force. And as the detail of the force, you can see we can input the magnitude here, but if you put down the number directly, it will just have the lifting force here, but the direction is differently with the normal direction of this space. But if you would like to assign a very precisely, very well designed vector, you can change the divide by to the components and find out the components, the components, and put the 9600 value into the component, and it will much more well defined. So after we have put down the geometry constraint and the pressure load and force load, we have well defined all the boundary condition we need, and we can click the solve here, and the part there is something here. It means you would like to solve the simulation, and if you click on the solve, it will solve the result. As you can see, there is some yellow sounder turning to the green, means it is calculating. And after your calculation, you will become the check mark. And if you would like to know the deformation result, you can insert, right-click on the solution and find out the insert deformation and the total deformation, or the insert stress with the equivalent, or insert stress tool with different kind of value stress theory, like maximum equivalent stress or column stress or maximum tensile stress with different kind of value theory. So you can using your right click and evaluate all results again, or you press the solve again and you evaluate all the results for you. As you can see, we can using the graphic viewer to check the result, and on the top of the view, here are some probe and the maximum, minimum indicator. If you press on the tag of the maximum, it will indicate the maximum value of the stress in this view. You can using the rotation to find out where is the tag and which region. So this is how we do the static structural analysis with Ansys mechanical. But for more detailing or more customized result, viewers are not showing today because our static structural analysis lecture is for 2 days training. So here we're just showing the workflow of structural analysis, about the material assignment, about the geometry import, about the condition settings, and the post-processing settings. You can see the result and you can play the result with the animations. As you can see, the deformation will, just as shown, it will deform very very high deformation, as you can see. So this is about the static structure, how we do the simulation. And after that, we have to save for the project. As you can see, there is a set project button here, and you can set to a specific path for the specific file format, as we call WBPJ. You can put down at the position you are assigned for, maybe like a demo 1. You can put down the name here, and we can press the save. Okay, that's it. We have finished a product structural analysis of ball bodies through the Ansys with the Ansys mechanical. Okay, this is about the static structural analysis. So as far, is there any questions through the analysis, or is there any things you would like to know, the limitation or the capability of this static structural analysis? So the workflow we have defined for the material, for geometry, for the model settings like meshing, load support, geometry, constraint, and the solution solving, and result validation. So this workflow, is there any problems or any questions? If not, we will go to the next analysis system with the model analysis. Okay. Okay. So let's go to the M09 linear dynamics. And in this analysis, we will know what is model analysis and the theory, about the theory and the assumptions, analysis settings and the solutions. And sometimes our model analysis would be affected by the static structural analysis. So sometimes we will need to consider about the pre-stress conditions. And we will know about these modules. We will have some overview. And first, we will know what is model analysis. There is some word here. A model analysis is determined the vibration characteristic. It is combined with two properties. One is natural frequencies, one is mode shape. And combined with these two, we call it a model. Of the vibration characteristic of structural and machine components is we would like to determine through the model analysis. It can also serve as a starting point of another more detailed dynamics analysis. Because when you are undergoing transient dynamics phenomena or harmonic analysis, all the dynamic event could be made, could be affected by this, could be based, supposedly they are based on the structural characteristic of the vibration characteristic. Like when your structural undergoing a dynamic event, all the dynamic behavior can be composite with the different models. So the model analysis is the basic and the fundamentals of all the dynamic analysis inside the dynamic problems. So if you do have any kind of dynamic problems, you would like to know the root cause, the reason, and you will need to solve for the model analysis. So the theories and assumptions are start with these equations as we mentioned earlier. In the motion, in the general constitutive equations of structures, we can reduce the force and the damping terms and into this form. It is called the linear equations of motions for free, undamped vibrations. Free means there is no load applied to the system. Undamped means we don't have the damped effect to the governing equations. So the equations will turn into this kind of a form. And when we reduce into this form, the solutions could be assumed to like a harmonic motions. As you can see, this is the 1 degree of freedom of the solutions. So if you put down. Here is a metric form. If you turn into 1 degree of freedom form, you can trace down with the MA plus KX if you are familiar with this kind of equations. And the solution is supposed to be like A sine omega t plus the phase shift equals to the x. The solution would be like this. This is 1 degree of freedom if you do have take the lesson of the vibration. You will learn about this solution very much. So we don't talk about this today too much. Okay. So the next, if the problem, we will reduce the problem into a linear problem because we would like to solve the model analysis very quickly because we would like to know the root cause instead of the nonunity. But if you do have some nonunity problems, you will using another analysis system instead of the model analysis. In the model analysis, we will focus on the stiffness and as well as the mass in some form. So because we would like to focus on the stiffness and the mass, so we have to define the stiffness of the material and the mass for the material. And for the mass of the material, it is affected by the property of the density. And for the stiffness, it is being affected by the isotropic elasticity or the Young's modules. As you can see, we turn it back to the every data. And if we would like to solve for this problem, you will need to assign the material property for this analysis. And you can see we have to define the mass through the density. So if you would like to define the stiffness, you will need to assign the isotropic elasticity for this material. It will compensate with the Young's modulus and the Poisson ratio. These two properties or three numbers must to be input for solving the model analysis. But if you are solving a static structural analysis, as we can see previously, you will not always need the math. This term is not required for the problems of the static analysis, but it is required for the model analysis. Okay. So in the problems, in the assumption of the model analysis, stiffness matrix and the density and the mass matrix are constant and are required for the simulation. On the other hand, the damping is not present because we are an undamped system. But sometimes we can include it with the harmonic analysis, considering the damping effects through the harmonic analysis with different analysis system. And the force are not present because for the model analysis we are solving for a free undamped problems as we mentioned earlier. So there's some fundamentals about if we would like to knowing what might affect to our natural frequencies, and during the fundamental questions, as we can see here, our accelerations is affected by the frequency is a square of the frequencies is very positive affected. As you can see, the equation here, it equals to 0. So your natural frequency is affected by the k divided by mass and root to 1 divided 2. So here are the affected. I think I can mark down some fundamentals. I think there are some contact type you should keep awareness that they will turning from non-linearity into linearity. So there are some assumptions here. I think we can skip all these, the rest part in. We can just introducing you with the real case, I think. So we can skip the rest part and into the workshop 0.4.1, 04.1. It's about machine frame, model analysis of a machine frame. It looks like this. It's a frame, and we assume that there is a machine put on the frame, but we don't want to put the real machine onto the frame. We want to reduce the machine because the machine is supposed to have a very a little bit higher natural frequency than the frame itself. So sometimes we will just reduce the geometry of the machine instead with a mass point to solving for to calculate the vibration characteristic of the structure. So the progress is the same. We can drag the model analysis onto the workbench, and you can using the same workbench view, and you can find out the model analysis inside the toolbox and click on it and drag to the green box. And for geometry, you can using the right click here and import geometry browsing and find out the path and the M09, M04, and find out the machine frame point STP file and open it. So after import the geometry, we can burst directly into the model because we don't need to assign the material because we will be using the default material. It's just for demonstration. And then the first very important step is that we have to define the most suitable unit for solving these problems. As you can see, we will assign the unit metrics with the millimeter, ton, Newton, second, millibar, and milliampere. So where can I find out the unit settings? You can browsing at the top tab, find out the home. And there is a unit at the middle. You can find out the millimeter and ton units here. This is one way. Only the second way is at the right button over here. You can find out the unit system here. You can just click and change the unit system. The unit system is very, very important. If you choose the wrong unit system and put down the same values and the meaning of the physics would have be changed. So we have to check. You have to check the unit first. And then the outline of material, you're supposed to check the material if they are the right materials. But somehow we don't change anything there. We're just using the default material with the structural. Still, you can press the plus here and find out every part and check the material assignment. And here we would like to assign, you can browsing down to the support. Here, as you can see. Here we would like to add the constraint to this machine frame. Our constraint is that there are some rod penetrates to the hole to fix the frame's movement through the holes. So we would like to add some name selection to pick up all the holes to add the boundary conditions to constrain the movement of this frame. So we would like to add 8 holes that can be filtered and add to the worksheet. As you can see, if we would like to pick up all the holes, you can using the pickup here one by one, or using the worksheet they have mentioned about. So you can using the selections here and turn into the worksheet. No, sorry. Insert them selection and into the worksheet. I would like to add a hold, copy the name a hold because I don't have the hand to type any word. A host, you can copy the name here. And the hole is supposed to, we want to pick up the holes, so the best supposed to divide by the radius and equals to 10. And we can see what will happen if we input through this 10. And we can press the generate, and that will add 8 holes. That will select the hole with the radius of 10. And if you using the best selector on this best, you can figure out the best is characteristic by the radius of 10. If the face had matches the radius of 10, it will be added into this selection. So the next, we would like to add the four holes of the selections. Four holes. It consists of the. We would like to remove the best location is at 3,200. So we would like to duplicate these settings. I'll just demonstrate it so you can just see what happens and what we would like to pick up. Here. I would like to add the remove of the just generate the four holes. You can see there is the four facets. One is here, the other one is here. Right. And the four holes is at the corner of this machine frame. Is four holes. And the second, we would like to insert the cylindrical support. As we mentioned, there is a rod insert into the hole, but the rod has not weld or stick to the hole, so we were using the cylindrical support to keep the possibility and the free motion of the tangential motion. So we will insert a cylindrical support onto the 8 holes and keep the tangential free. It means it is rotatable, but it is constrained to the shifting movement. So we were using the insert of the cylindrical support, and we will select to the next selections, to the 8 holes, and keep the tangential free. And it is quite important if the parts are not modeling into the geometry, but there is some connection, constraint, and degree of freedom supposed to be constrained appropriately. And the next, we can just we should set how much modes we would like to figure out. And defaultly, it would be put to the 6 as the lecture materials dedicate. So you can just solve it now, and it will create the mode result for you. And after you solve it, you can click on the solutions. It will show it out that there is the first 6 modes of these problems is made of 33 frequency at the first mode, and 110 on the 6th mode. And if you want to check the mode shape, you can pick out the blank here, click on the blank here, and right click, and pick out the second items. It will create 6 results, and you should put the solve again. And they will show it up each mode separately. At the first items, you can see the mode 1 shape as shown. If it is too much black line of the element, you can turn off the wireframe element frame and show up the deformations, distributions of this mode. But in the model analysis, the magnitude is just relatively magnitude. It is not real meaningful values. The meaningful is about the shape, but not the deformation value. This is different things. If you would like to have the real magnitude that are affected by the real load, suppose you have to pick out the different dynamic system to analysis for that kind of problems. Because in the model analysis, we would like to know is about the mode frequencies here, because the mode 1 is being induced by the 33 frequencies, and the shape of the mode, not the magnitude of the mode. It is all about shape. Because as you can see, the deformation is 9.4. The maximum deformation is 9.4 millimeter. If we clear the generated data and we change the matrix and solve again, the total deformation value will be affected into a approximately 0.3 meter of the value. But as you can see, the shape is the same, but the magnitude is affected by the unit. It is nonsense because in this model analysis, we were using the unit vibration to affect it on this model. So it is important that the value is not meaningful. The shape and the distribution is the most important in the model analysis. So through this analysis, you can see if we had constrained the hole with the cylindrical support at 8 holes at the two sides of these machine frames. As you can see, it will constrain. So the rod here, you can see the part named crossbar 1 and crossbar 2 are well constrained. So it always has close to the visual deformation at the two sides of the machine frame. But if we don't constrain with 8 holes, we only constrain with the 4 corners of the holes. You can see the effect to the machine frame through these settings. As you can see, at the first 2 modes, there is no much difference. But at the third and the fourth mode, the frame had deformations at the two sides that would have effect and up and down vibrations here, and you can check the vibrations through this Ansys mechanical software. And you can compare these two results to duplicate the analysis system and apply with two different kinds of analysis settings and solve. And when dividing the screen with two directions, the top is the 4 holes constraint at the fourth mode. And the bottom is the 8-hole constraint with the force mode. As you can see, this mode with the similar frequencies but with different kind of constraints. The vibration mode, the shape of the vibration has different at the side, at the two sides of the machine frame. So with the structural analysis, you can see the different constraints might affect it to your design. And if you would like to use the experimental tests, you might need to prototyping with this wood machine frame, and you might need to have vibration test machines and design the fixture and input the right frequency swap range, and you can find out the simulation result. You can find out the structural result, but through the simulation software, you can just using your 3D file, and evaluate your result, validate your mode shape and more natural frequencies through the software, and you can reduce a lot of time through the software. So beyond of this, visually simulation result, you can check with the degree of freedom result or the participation factors. Here you can find out the participation factor summaries. You can find out each mode might have a ratio of effective masses or cumulative mass matrix fractions. What is the ratio of effective mass to the total mass? It means when the mode 1 happens at these natural frequencies, the shape is tend to vibrate through the y directions mostly, and rotate. The behavior will rotate at x and z directions at mode 1. What does it mean? You can check the number and log number and comparison with the shape. As you can see, we can close the view. As you can see, the vibration is up and down, which means we are vibrate at the y direction. So you can check with this result. Y directions has a magnitude with 0.5. So the x directions has the less values, and z direction has a less value. And for up and down, if you do treat the two sides of the fixture as an axis, and relative to the axis, it is like x rotations or z rotations. If you treat these 2 points as an axis, it will like a z rotations. So as you can see in the partition factors, in the ratio of effective mass, you can find out the rotation x, and rotation z has some values here. It means your shape is tend to vibrate at y directions and vibrate with the rotate x and rotate z. And it is quite important if you would like to find out the similar mode shape with the value instead of a 3D shape, because if we're using our eyes to check if two shapes are similar, we were using our eyes. But if we want to using some values to check if they are tend to behavior at the same motions or specific directions, you will need to using this total mass. And instead of this, supposedly one part or one structure, they tend to have any kind of movement in one directions. And those kind of movement like when I'm walking on the street, or I'm walking through here, or I raise my hands, every kind of my motion can be made of my mode shapes. You can characterize your emotions by the concept of the mode you figure out through the model analysis. So when you would like to figure out all the possibility of the y direction movement, you supposedly to find out the enough mode they can max the y direction of the sum of the ratio effective mass to the 0.8, and you can find out the mode shape that can compensate of your motion through these values. So if we would like to find out all the y motion, they would have possibility to compensate your y motions. It is not enough. You have to find out more modes you need to find, maybe 12 or maybe 20. If we put down the 12, you can see, I think this is not enough more. But as you can see, the sum of the effective base is not increasing obviously. So we can check the result. Supposedly there is no y direction movement in the 7 to the 12. As you can see, the shape is like this, but the effective factor is not quite. It's not quite. Not quite effective to the motion of y directions, but it's not quite. It has less possibility to occur. When the value is low, it means it is less important to the behavior. If the value is high, it is tend to be triggered through your law. And what does it mean? If you do have any damping, maybe the frictional or some additional effect like wind or like the additional loading, this mode is highly possibility to be removed. When the value is high, it is hard to be removed. So if you put the damp effect into the mode analysis or into the real problems, this kind of vibration will be reduced or be eliminated. It is high possibility to be eliminated. So the most important is the mode that has a significant values. Significant values in this 6 degree of freedom sphere. So it is important to figure out your mode is meaningful or not meaningful through the numbers here. So if the number is above the 0.1 percentage or 1%, and it is an important mode. But if there is not any values is above the 0.1%, like this mode, 133. There is no value is above the 0.1%, and this mode is not significant, not important. You can just skip this mode because it is less possibility to happen. But somehow, if your load is, if your force is very large at the direction of its vibrations, and still it will be triggered. But it is easily to be bent and to be eliminated through your bending. And so that's our lesson today about the static structural analysis and damping analysis. We will be using the tools to check and validate your structural design through the software. And for moreover, if you are very interested in this workflow and simulation, and you can take our lessons course be held by our companies. You can check by our website, or you can learn with free and with the Ansys Innovation Space. And thank you for the day.